Hi, today we're going to talk about a very special topic, which is imbalanced data. Although we have mentioned some upscaling, downscaling package before, such as SMOT, but in Keras, there are some other interesting techniques that can help us to analyze imbalanced data. So here we are. And please take a look at this code provided by Google TensorFlow. Okay, the dataset we use right here is credit card fraud detection. Okay, so here, as you can see that it is a very imbalanced data. Okay, we have only 492 fraud transaction, and just like a normal, just like the data set we collected in the real world, most of the transaction in this data set is normal transaction. Okay, the total number would be 284,000 transactions in total, and we will show you some interesting techniques to learn from the imbalanced data. Okay, so here is the some packages we like to use. Okay, and a very interesting thing is that the dataset provided by Keras, it has, as you can see, that it has a lot of features, but we don't know what exactly they are, because the name is quite interesting. Okay, V1, V2, V32, V28. Okay, so we don't know what exactly it is, but it has two different labels. Okay, so that is okay. Before we introduce some techniques, first we would like to calculate an interesting value, which is negative and positive samples. And here we have a rate. Okay, the negative samples is 492, and in total it is 284807. So these two numbers, okay, we will use these two numbers. And as we can see that it shows a small fraction of positive samples. And in this example, the positive means fraud. Okay, because we like to detect fraud, so positive is fraud transactions. Okay, so that's quite normal. We split a claim and normalize the data. Okay, I think that is interesting and important things. Okay, so here we divided split data, okay, into several different data sets, including training, validation, and testing. Okay, so if you directly apply those data sets by using the machine learning or neural network algorithms we taught before, it is likely that right here, it is likely that your model may always output the detection, the prediction as negative. That is because more than 99.8% of the target value is negative. So it is very difficult for your algorithm, no matter it's an ML algorithm or it is an algorithm, to learn how to output a positive target value. Okay, so here is the number of training data set, validation data set, and testing data set. Okay, so we can see that. Okay, so before that, okay, one interesting and important thing is that before we process this data, we apply a standard scatter before we apply any algorithm, because we don't know what exactly those features, original features, V1, V2, V3. It seems like it has some positive values, negative values, and some values is very small, some value is very large. We don't know, but it really doesn't matter. So we apply standard scatter before we start our analyze before we start analyzing our data. Okay, so the first thing is how about take a look at the data distribution. Okay, so as you can see that we have some unknown features V6 and V5, and here we have the positive distribution of V6 and V5, and it seems like some value is right here in the middle of the plan of V6 and V5, and you can see that for negative distribution, negative means normal transaction. Okay, for those normal transaction, it seems like we have only two cluster, but it is just some interesting visualization tools to help you to observe your data. Okay, so here metrics. Okay, in the past neural network code, most of the time we output accuracy and loss value when we train our neural network, right? But actually there are tons of metrics, including the values in our confusion matrix. Okay, true positive, true negative, false positive, false negative. You have the accuracy value, precision, recall, and AUC values. Okay, so for your convenience, I strongly recommend you write your matrix in this way as a list. Okay, and further, right here, you can simply just input this matrix as the parameter of your compile function, so that every time you run an APAC, okay, those values will be calculated. So that is very convenient for you to observe what is the current performance of your model. So you will have those matrix value. Okay, so next thing is that it is very interesting that here we have model, right? It is a very, because it is an just tutorial, so it is a very simple sequential model. We have dense layer with 16 neurons and ReLU as the activation function, and a drop out layer and the dense layer to output a value. Okay, it has only one neuron because it has a sigmoid value. So if it is larger than 0.5, and that would be target y as 1, right? And if it is less than, if this value is less than 0.5 after sigmoid function, then that will be the data will be predicted as target 0. Okay, but there's a very interesting things that we have a bias initializer right here. Okay, we will talk about it later. Okay, but that is a very interesting things. Okay, so right here we have the definition of true, false, accuracy, precision, recall, AUC precision. So we have talked about before. So make sure you understand everything about it. Okay, so right here since we don't know how to how many epochs we should use, so here the tutorial set it to 100. But it is a very interesting is that the batch size, if you don't set the batch size, the default size is 32, but the batch size right here is 2000, right? So let's take a look at our data set. The data set has more than 284,000 data, right? And if we use a very small batch size, it makes your neural network, when performing gradient descent, it needs a lot of calculation to perform gradient descent, right? So in this case, we encourage, okay, we strongly recommend you increase the size of batch size. That is because every time it can decrease the number of partial differentiation calculation in one single epoch. That is reason number one. And reason number two is that if your batch size is still 32, that means every time when you randomly get a batch from your training data, if the batch size is 32, it is unlikely that you get one single positive sample, because your positive sample is quite small. So if your batch size is 32, most likely all those 32 samples in your batch, they are all belongs to negative sample. So that means when you do gradient descent by using this batch, it has certain bias that your when you perform gradient descent, right, you have a target value, right? It is either MSE or course entropy, right? It is likely that your current direction of your gradient descent is not that good, because you have only negative data to perform gradient descent in this single batch. Okay, so if you increase this number, okay, to 2048, you have more chance to sample positive data, right, in this bigger batch size. So in this case, when you perform gradient descent in this single batch, the direction of the batch, the direction of gradient descent would refer to some positive data and some negative data. Okay, so we recommend that you increase this batch size. So that is I write it here. Okay, so ensure each batch has a decent chance to containing a few positive samples. Okay, so since we don't the next thing is, since we don't know how many batches we should set, so we have a callback function. The callback function will be called after each epoch, right? So early stop right here, it means we like to monitor the validation precision. The patient 10 means in 10 epochs. Okay, the mode max means if within 10 epochs, if the maximum value of validation precision does not increase, and then we should stop training, no matter how many epoch you set right here. And after that, we should restore the best weight. We will see how it works later. Okay, so that we can see that it's a very simple sequential model. Okay, but before we fit this model, okay, we can make very interesting things that we try to predict the first 10 samples in the training data set without trained model. Okay, so that so ideally the weight is from a random is random. Okay, the bias is random, so the result of such kind of random model, random weight model, the result of the prediction should be random. But as you can see that since we use sigma as the last activation function, right? So you can see that there are some code. You can see that this one and this one. As you can see that lots of samples in the training data, okay, when they enter this random weight model, the output says they are larger than 0.5. So the target Y value of this data should be 0.1, right? Only this one, 0.34. Only this sample, its value is less than 0.5. So the predict value is 0, right? So as you can see that is that really reflect what we is really reflect the sample we have? Usually it is not, because the weight, the bias is just a random number, random value. So that we can see that those initial guesses are not great, and we know that the dataset is imbalanced. So some people right here, okay, it says you can do some tricks, okay, on your bias, initial bias. So here is the how it works, okay. Since we know that the probability of zero means positive, the probability of zero positive is this one, right? The number of positive samples over total samples, right? Okay, that is the probability of positive. Okay, and as you can see that at the last, our sigmoid function looks like this, right? So if we simply just if the weight are all zeros, that is an assumption. If the weight is all zeros, and we can see that only B zeros right here, that means the initial value of your bias. Okay, so if it is looks like that, okay, and you can see that B0 should be set to this number, okay, and this number is minus 0.35. That again, let me explain it again. If W initially it is a random, then we assume it is 0. Okay, assume it is 0. So if we want the output of our sigmoid function, okay, so right here, we're very close to the probability of the positive samples, which is P0, and the initial B0 should be set as this value. Okay, so we calculate this value. Okay, so as you can see that if we calculate this initial bias, which is minus 0.39, and we use this initial value in our model. So let's take a look at this code, right? I think right here. So here you can see that line 14, 15, and 16, if input bias is provided, and you can see that the input bias will be used to construct the model at line 22, right here. So we could do a very interesting test. I think it's right here. So the first one is we use a model and we set its bias to all zeros. So that is a bad model, okay? And the second one right here, we create the model again and use the initial weight. We calculate from this from here. Okay, so we have two models and we train the model. Okay, and again you can see that right here, the orange one right here. Okay, the orange one is the careful bias right here. This is the careful bias. Okay, and the blue lines right here is the zero bias, and the dot line and the solid line, they are training data and validation data. As we can see that if we carefully assign the bias by using this concept, okay, it's right here, by using this concept, you can see that its starting loss value will be lower than the blue lines. Those blue lines, their model are BIOS initiated with all zeros. And as you can see that while we performing gradient descent with different epochs, you can see that it decreased more faster, the orange ones. So if we carefully design the initial BIOS, and your model will start with a lower loss value. Okay, that is because your initial output, okay, initial output will be close to your samples, which means if you have only 1% of y, 1% of target value equals y, and right now, using the carefully designed BIOS, your output will output initially, okay, without any training, its output will very close to 1% of output y is equals to 1. So that your loss value, okay, so you can see that we can calculate those initial loss right here. That is the definition of cross entropy, okay, and we have the probability of P0, which means the probability of positive. So it is a lower value, lower loss value compared to you use a random BIOS. Okay, so that is one of the very useful technique you should use. Okay, so that is the first techniques. Okay, and we train the model, and after that we can see that right here we don't have to run all the 100 epoch, because in these cases, okay, we can see that within 10 epochs, the precision value, the validation precision, okay, sorry, I think it's right here, okay. The precision value of the validation data set does not increase within these 10 epochs. So that means the model just stable right there. So you can stop at 49 epochs. You don't have to run the rest of the epochs. Okay, so that is the okay, I think that's right here. Okay, so you stop earlier somewhere right here. Okay, that is because you're I think is precision. Okay, so you don't have to run off the epochs. Okay, so that is the technique number 2, and you can see that after that, because it's imbalanced data, so you can see that the number right here is so imbalanced. Again, then that is of the metrics we defined before, and you can see that because we use sigmoid as our last activation function, so 0.5 means you use 0.5 to divide all the target value, right? To identify if they are label 1, class 1, or class 1, or class 0. Okay, but since it is a imbalanced data, so sometimes, okay, so that is the PRC. How did you calculate all this value? Okay, just copy this code. Okay, and that is AU PRC. Okay. Okay, so that is how those works. And the next interesting thing is that the class weight. So basically that you simply just run this code and get the weights of each class. Okay, so you cannot change these values because it is calculated from some mathematic theory. Okay, so basically since you know your data is quite imbalanced, so when we train our model, you can provide this value right here, line 12. So when your model to run epochs by epochs, when they retrieve the batch the batch to train each epoch, okay, this class weight will try to tune how many different samples they should retrieve from the original training data set. Okay, and you can think in this way. Since we have very little few positive sample, right? Positive sample. So the training weight of this class is larger. So when you perform fitting, you should retrieve more positive samples. So TensorFlow or Keras will do so for you if you provide class weight. So you don't have to perform upscaling or downscaling by yourself. It is a very convenient way to deal with imbalanced data by using class weights. So make sure you understand that and you use it if you encounter a very imbalanced data set. Okay, so it is automatically to balance the data. Okay, so right here. Okay, and it stopped right here. So because we have already stopped. So you can see that it is still looks quite good. Okay, and here's the matrix. Okay, and here's the PRC, here's the AU PRC. Okay, and of course you can perform oversampling by yourself, but I do not recommend you do so because we have more powerful package that's SMOTE to do so. So you don't although this code is provided by Google, but I do not recommend you perform upscaling by yourself. Okay, so but here we will skip this part, but if you want to take a look at this code, upscaling code, just take a look at this. Okay, so here's the oversample data, so here's the result, and again it provide those figures and metrics. Okay, so let's stop here. So that is an interesting code. It provides a lot of techniques. So the reason why we talk about this specific code is because next week when we talk about anomaly detection, usually in the real world when we collect security data from some source, it is very likely that we only have very limited attack data. And most of the time when we collect data, they are all normal data. No matter, for example, packet we talked about last week. Most of the time when you collect data from your firewall, most of the packet are normal packet. Only very limited packet, very small amount packet is attack packet. So that is how so we introduced there are some good techniques you should use when you analyze such kind of imbalanced data.